Okay, so now we are looking at the end result. We are looking at the current equation for the circuit containing of capacitance, capacitive current, a passive conductance, the passive current through passive ion channels, and also the synaptic current, the red current, which is the synaptic current. The sum of all these three in a closed circuit without external current should be 0. If I inject current I, then I should write I. But since I don't inject to cells usually, unless I'm an experimentalist and I want to inject current, but usually I don't, then this is the current equation for the synaptic current total. And if you solve this equation for V, this V will be the voltage change due to the activity of the synapse. Then you get this equation where you see in this part, which is the steady state part. Let's not look at this part yet. Only this part is the steady state part. You see that the contributors for the voltage is the conductance related to the passive battery, so G rest multiplied by E rest, plus the synaptic conductance multiplied by the synaptic battery, and the summation of the two. And this relationship tells you what will be in the steady state case in case the GS and the GR are steady open and you wait enough time. This is the voltage that will be developed in this system. Let's take the case where the synaptic conductance is 0. No synaptic conductance. In this case, this is 0, and your voltage will be your resting potential. This is your minus 70. Suppose your synaptic potential is very, 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 very strong. Suppose the G synapse, the conductance, the red conductance due to the synapse, the GS is very, very, very strong. This means that this is very big compared to that. This is very big compared to that. And you will stay with GS divided by GS, which is 1. You will stay with this, with ES. Okay, so this means really that in this system, the two extreme will be either when the synaptic conductance is 0, then you get the resting potential, or when the synaptic conductance is very strong, then you will get the full synaptic battery. And this is where the synapse can move. This is where the voltage of the synapse, we can call it Vs, the voltage due to the synapse. The voltage due to the synapse here will move, will be shifted between the resting potential and the synaptic battery, somewhere between. So this is something important to remember, that in the nervous system, because you don't have an external current, and everything is coming from within the system, and the system is built or changing voltage due to changing conductances, you will always be limited by the related batteries. It's because with an external current, you can get any voltage that you want in principle. If you have R and multiply big I, you will get big IR. But here you don't inject current from the outside. You change conductance. You change conductance for a particular ion. This means that you may express more or less a given battery, depending on how strong your conductance for this battery in the circuit. So this is very important. This means the following. Let's look for a second at the voltage scale. Let's say that this is your E rest. This is your resting voltage, let's say minus 70 millivolts. That's where you start from. The cell always sits here. Now suppose you have a positive battery here. This positive battery may be the battery due to the opening of sodium channels. It will be a positive battery inside, because as we said before, sodium tends to go from the outside to the inside because of this drop or this change in concentration. Very big outside, small inside. So in this case, if I open a conductance G for the sodium, my voltage will start to grow this direction, because the battery of the sodium will be more and more, if G of the conductance for the battery for the sodium will be strong, the voltage will go there. So your synaptic potential will be depolarizing. Suppose you have another conductance, synaptic conductance. This will be your battery, let's say for the case of potassium. In this case, whenever you open new conductance for the potassium, your membrane voltage will go below the resting potential, more negative or more positive depending on the battery. This is exactly what is written there. So this is what we will call depolarizing synaptic potential. This is what we will call hyperpolarizing synaptic potential. This will be, again, depolarization, less depolarized than the resting potential, and this will be hyperpolarization, more polarized, hyperpolarization. And this is what the synapse can do. Some of the synapses will be depolarizing synapses, depending on the battery. Some synapses will be hyperpolarizing synapses, depending on their battery. But that's what they can do, and they are limited by the battery. You cannot get more voltage than the battery. You are limited by this ceiling. There is a ceiling to the synaptic voltage. The ceiling is the battery. Maximum you will get the most positive battery, or maximum you will get the most negative battery, depending on what conductance is being opened. And that's what the synapse can do. And just to summarize what we just said, is we said that in your brain, there are these batteries, which depends on the ion concentration of sodium, potassium, chloride, calcium, not many ions. But the concentration difference of these ions from inside to the outside determine the batteries. And these are the ceiling or the floor where the voltage of the synapse can go. It can go either so much positive, and it can go so much negative. No more negative and no more positive. That's your brain limitation. That's the signal that the brain can generate with synapses. And just to tell you that the maximal one could be something, let's say, like 200 millivolts or something like that, more positive than the resting potential, something like that. Most negative could go maybe to minus 90 or minus 100 millivolts, more negative than the resting potential, so minus 24 millivolts more negative. So you really cannot go much. You can either go this direction by minus or 20 millivolts. You can maybe go this direction by plus 200 or 250 millivolts. And that's the limitation of your signal in the brain. The brain cannot generate 110 volts, or in Israel 220 volts. It can only generate few hundreds of millivolts, maybe 200 positive, maybe minus 90 negative. That's all. That's all. So that's the regime of signals in the brain, and these are the signals you have to deal with in order to represent the whole world. The whole world is represented by signals that are moving between these two extremes because, just because, you are dependent on opening of ion channels, the signals in the brain mostly. This is true also for the action potential, the spike, which we will discuss next lesson. It all depends on opening of ion channels or closing of ion channels. And these ion channels are for particular ion, for example, sodium or potassium or chloride or calcium, and this is signified by a battery. And this battery is not too big. That means that you cannot get more than this battery, maybe plus 200 for calcium, maybe minus 90 for potassium, but that's your limitation. So these are the signals in the brain. This is the steady state case. The transient case depends also on this part, which you can see that develops the synaptic potential, takes time to develop. So there is a time constant for the synaptic potential. We don't need to discuss it now, exactly the equation, but in principle you understand whenever you open a conductance like this for the synapse, this is your synaptic conductance, and you measure the voltage in the circuit, you will get the synaptic voltage. It could be when you open this conductance, you will get a synaptic voltage that looks like this, because you open the conductance for a given period of time and then it is closed. The transmitter interacts with the receptor for a short period of time. Then you'll get the synaptic voltage here, V of the synapse. It will look like this. If it's a positive, if it's a depolarizing signal, it will go more positive than the resting potential and it will attenuate. I will call it excitatory post-synaptic potential typically. This is one case. In the other case, when the battery is reversed, if the battery is reversed and it's more negative inside, then when I open these channels, when I change the synaptic conductance G, I will get a negative voltage. I will call it inhibitory post-synaptic potential. It will go from the resting potential more negatively, and then will attenuate back to the resting potential. This will be my post-synaptic potential, which is hyperpolarizing. I will call it inhibitory postsynaptic potential. And then this one will be a positive postsynaptic potential, excitatory. And these are the two synaptic potentials in the brain. You have two types of synapses. We already discussed it last lesson. Some of the synapses tend to do negative voltage. Some synapses tend to do positive voltage relative to the resting potential. Typically, we will call those that are doing positive voltage inhibitory. They tend to inhibit the activity of the cell. We'll discuss what does it mean. And then you have some of them, many of them, that are excitatory, that tend to excite the cell to make it more excitable, more firing. The cell will be more active when you have a lot of them and less active when you have a lot of them.